Okay, this graph is going to talk about graphing polynomial functions and some of the things you need to remember in order to do that. The basic graph of f of x equals a times x to the n. This is kind of like the leading part of any polynomial function. If we have just a coefficient and x to the n, if we could kind of look at a couple of just kind of graphs that kind of build their way up. If we have the coordinate plane here, graph of, let's say a is equal to 1 and x to the first. So f of x equals just x. We remember that is the line. It goes through the origin, increases for across its entire domain. Let's do another power. Let's just increase the power each time by 1. So if I said f of x equals x squared, 1x squared, we know that is the parabola. Okay, so it looks a little different. It's decreasing on one side, increasing on the other. Okay, so if f of x is equal to x cubed, we know that that is increasing across its entire domain also. Let's raise it to another power. Let's go to the x to the fourth. X to the fourth is going to look similar to x squared. It's going to have a vertex point, but it's actually going to kind of be a little bit flatter, not as sharp, a little flatter across the bottom. But again, you're going to have the decreasing and increasing, so the symmetry across the y-axis. It's an even function. We talked about even and odd functions. Let's look at another one. F of x equals x to the fifth. X to the fifth is going to look very similar to x cubed, except you're going to be more flat across the bottom. You're going to go through the origin as well. Okay, so it's not going to be as steep. And of x to the sixth would be just like the x to the fourth, so it's going to be more flat across the bottom. Now those are some basic curves just to kind of look at and see how, but you can see the difference between even and odd functions. Look, the odd functions here, like x to the first, x cubed, x to the fifth, increase for most of their domain. You have the symmetry with the y-axis and the even functions. So a lot of that stuff holds true on through graphing polynomial functions. Graphs of general polynomial functions. As with quadratic functions, the absolute value of a in f of x equals a times x to the n determines the width of the graph. If you have a number that's greater than 1, the graph is going to be stretched vertically. In other words, it's going to be more narrow than it would have normally been. If the number in front is a fraction between 0 and 1, the graph is going to be shrunk or compressed vertically, making it open wider than normal. Graphs of general polynomial functions. Compared with the graph of f of x equals ax to the n, the following always hold true. The graph of f of x equals negative ax to the n is reflected across the x-axis. We've already talked about that with the other basic curves. The graph of f of x equals a times x to the n plus k. You're going to move the function up. If it's plus, if it's minus, you would move the function down, shift it vertically, up or down. If there is a number added or subtracted in parentheses, remember that's a horizontal shift. The graph of f of x equals a times x minus h to the n is translated h units to the right if h is greater than 0, and h units to the left if h is less than 0. So if this was a plus sign, we would do a left shift instead of a right shift. This is very similar to what we studied when we were talking about basic graphs, basic curves, basic functions. The graph of f of x equals a times x minus h to the n plus k shows a combination of all of those translations. Zeros are where your function crosses the x-axis. The behavior of a graph at a zero depends on the multiplicity of the zero as determined by the exponent on the corresponding factor. If you have a linear factor that is a zero, or a number that is a zero, if its multiplicity is just 1, it actually just crosses at that point. The graph crosses the x-axis at that 0 if it has a multiplicity of 1. So it just goes straight through it. If it has a multiplicity of evenness, for example, a multiplicity of 2, 4, 6, 8, so on, the graph is tangent to the x-axis. It does touch it. That is a 0. It does touch there, but it just bounces. It does not cross. It touches, but it does not cross. It come up and touch, but it will not cross the other side. If your multiplicity is odd, the graph crosses and is tangent to the x-axis at C0 if C is 0 of odd multiplicity greater than 1. For example, if you had a multiplicity of 3 or 5, it's going to cross, but it's also going to be tangent. The book uses the term it wiggles. The graph will wiggle at the 0. So you're going up, you're touching it, you're going through, but you're actually kind of touching it also at the point C. Turning points and end behavior. The graphs exhibiting functions of odd degree and even degree show that polynomial functions often have turning points where the function changes from increasing to decreasing or from decreasing to increasing. A polynomial function of degree n has at most n minus 1 turning points, with at least one turning point between each pair of successive zeros. As you go across the x-axis, you should have at least one turning point between each pair of zeros that you have. So let's say you have a function of degree 3, a cubic equation. You're going to have at most no more than 2 turning points in your function. End behavior is very important with polynomial functions. The end behavior of a polynomial graph is determined by the dominating term, the leading coefficient. That is, the term of greatest degree. A polynomial in the form f of x equals a sub n x to the n plus a sub n minus 1 x n minus 1, and so on in descending order, has the same end behavior as f of x equals a sub n x to the n. So this term right here in the front makes the whole difference about the way that the polynomial's end behavior is. End behavior of graphs of polynomial functions. Suppose that ax to the n is the dominating term of a polynomial function of odd degree. If a is greater than 0, in other words, if a, your coefficient, is positive, then as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, the function approaches negative infinity. The end behavior of the graph is much like the end behavior of a cubic equation. So it's going to go down and then up. On the left side, if your coefficient is positive, on the left side you're going to go down. On the right side you're going to go up. So if a was a negative number, what do you think would happen? It should reverse that. Like the reverse of the x cubed equation. Suppose that ax to the n is dominating term of a polynomial function of even degree. If your coefficient a is positive, then the absolute value of x goes to infinity, or positive infinity. The function goes to infinity. Therefore, it's like the x squared function. It goes up on both sides. On both ends, it's going to go up forever. If a was negative, guess what happens? It goes down on both sides forever, like even symmetry there, like the x squared graph. That's the end behavior of it. So let's talk about a couple of functions and decide what type of ending behavior the function would have if we graphed it. Describe the end behavior of the graph of the function. So my leading term is x to the 7th. Since the coefficient is positive on that, that means since I have an odd degree, then it's going to be like the x cubed function. The end behavior will be, on the left side will go down, and all this stuff happening in between, but on the other side, it'll go up. Now, had that been -4, it would be opposite. It would have went up on the left side and down on the right. This is because your power is odd also. Let's do one more. If I were going to graph this function, -10x to the 6th minus x to the 5th plus 2x minus 2. The dominating term is the first one here. Since it's an even power, it's going to have the x squared end behavior, either up on both sides or down on both sides. Since the coefficient is negative, this one would